the clocks are kind of off between the computer and one of those clocks over there is quite a bit different. So it kind of throws me off there. So when we describe probability distributions, we have to give probabilities or formulas or things like that for it. And for discrete ones, random variables, you can give the values for x in the set of possible values. And so maybe this is, little f of x. It's sometimes called the probability mass function. Because there's a chunk of probability at each point. And for something like binomial or Poisson, we really give that by a formula. Right? Another way you can get a lot of that same information is the probability that x is less than or equal to value. And this is really called the CDF, or cumulative distribution function. Another primary way of just giving information about what distribution you're using is this this moment generating function for a random variable. So for almost every distribution what we'll encounter, the probability distribution has a corresponding moment generating function. It was the expectation of e to the t x, so expectation of that particular function. And they have some uniqueness. So if a moment generating function exists around t equals 0, it doesn't have a discontinuity or strange thing happening, then it corresponds to a probability distribution, and there's only one probability distribution that corresponds to. And there's some other things that we'll do with that, like if you have independent random variables and add them up, you're multiplying the moment generating functions, and so it's one way to get at figuring out what is the new distribution. Right? If you know the new distribution, you can have means, variances, and things like that. The book also mentions something called a probability generating function. We're going to, it's also something that uses imaginary numbers called the characteristic function for probability distribution. So there's a couple of other things of these kind of summary functions that then get especially associated with them. So in probability theory, at the graduate level, you look at more of these things and how they work a little bit more. We can figure them out for some distributions and do a few things with them. So we have all these distributions, and you have one way or another of describing the distributions. But when you come to an actual data example, a question becomes which distribution is appropriate? Which one would you actually use in an application? Well, some of it depends on the kind of the process which you get data. Right? If it's a binomial experiment, you have a certain number of trials, you have a constant probability, and if you think the observations are independent of one another, it fits that binomial situation. It fits the assumptions, so it should be appropriate. But then you might ask, well, if you know some more information and can divide the subjects into groups, is it one binomial or is it different? Are there really different subpopulations in there? And it's something that just kind of depends on the situation. Right? The Poisson fits many cases where you have a very large population and things happening at some small rate of things happening, and it might or might not fit. Right? The course that's in the fall, course Statistics 252, which is kind of a natural one to follow after this one, is mathematical statistics. It deals very extensively with that idea of does a probability distribution really be appropriate for data. is there goodness, how well does it fit the data? How do you make decisions about which distribution to use? How do you look for discrepancies and things like that? Or in a number of these distributions, there's parameters. Like there's a proportion, there's a Poisson rate, right? When we get the normal distribution, there'll be a mean and variance. How do you estimate those things from data? Right? If you don't know them, but just have a sample, how do you go back and figure out what the parameters probably are and what distribution it might be? That's what mathematical statistics really is concerned with. Right? So anyway, looking at Poisson distribution as one discrete, and then the moment generating function on that homework, a few things to do with it. Right? Okay, so in terms of the course plan, Thursday, we're going to do a little bit of review for exam 1. Right? And then Tuesday next week is that exam 1. Exam is in class. It covers these homeworks 1 through 5, the 4 that we've done, and then the one that's due tomorrow. I'll post some practice problems that we'll look at. For the exam, you can have 1 page of notes, just one side of a piece of paper. You write down formulas for distributions, numerical examples, whatever you want. Verbal explanations of different things, but a lot of it will be formulas or examples. Calculator. So a calculator that can allow you to do the type of calculations, e to a power, multiplying numbers together, dividing. Not too overly complex, but kind of like the things that we have there. Right? So I'll post these practice problems, and we'll talk more about what's on the exam on Thursday, and have some things for you to study over the weekend. That's where we are today. We kind of move essentially beyond what would be on the exam. We start looking at the next chapter. So in chapter 5, concerning continuous random variables. When the thing that we're measuring is not on the integers or not a few categories, but is more of a continuous measurement like height or weight or concentrations of chemicals or something like that. So if x is a continuous random variable, we have to describe it somehow. Okay. The probabilities associated with this don't occur at particular points, but there is what's called here a probability density function. That describes the likelihood of different values. And so this f of x is just a continuous function. It can have different forms. Right? And so the height of this is f of x. And it is a probability density function if, so these are the values that we might see over kind of continuous range. The densities have to be greater than or equal to 0. And if this describes probability, and the integral over the whole real line dx over the whole real line, which is negative infinity to positive infinity, dx is 1. And so the probabilities that you're between any 2 points, right, so if you have a point here A and B, the chance that your value x is in this between these 2 points is going to be the area under the curve. Right? So the probability that a random variable x is between 2 points, right, there's going to be an interval between the limits of f of x dx. So when it was discrete, I can give you probabilities at individual points, but this one's continuous, so I can't give you probabilities at individual points. I have to give you this density. It kind of gives you the relative height, relative likelihood, and we get probabilities by integrating over areas. Any questions about? Now with discrete, it made a big difference whether it was equal to something or greater than it. Right? Greater than equal and greater than made a difference because it excluded one particular point, assuming there was some probability at that point. For continuous, what's the probability that we're at exactly a value under this curve? Is there any probability at a particular point? Is there any area underneath a curve at a point? No, there's none, because there's no area, right, at an infinitesimally small point. So when we have questions with continuous ones, we're a little bit more relaxed about limits. So this is the same thing we would compute if we do just less than, right, those two. Because there's no, of course, when we have a real application and you're actually measuring something, you tell me a number. You tell me height in inches. You tell me weight in kilograms or something, right? So you tell me a number. So things do happen, but kind of theoretically the chance that it's a particular number. Because with the continuous ones, we can vary it by 0.00001, and that's another possibility, and anyway, it's a little more relaxed. So discrete, probability at points, and the corresponding thing for continuous is this. We also can get a cumulative distribution function. Right? Another way to describe the random variable x is with its cumulative distribution function. It's the probability that x is less than or equal to x. And so that is an integral going all the way down to negative infinity, possibly, up to x of the density. And so because the limit, as I write it up there up to a value x, right, is there, I don't want to put x inside the equation, so I usually put a placeholder in there to make the integral work out. We'll see one or two examples like that. Right? As x goes to negative infinity, the cumulative distribution is going to 0. And as the limit of x goes to positive infinity, f of x is going to 1, because the area under the curve is 1. And this thing is increasing. So the cumulative distribution function comes along here for a while, possibly at 0, and then it slopes up, and then it curves out. It asymptotes at 1, and an asymptote line there. And this is f of x. So that's the cumulative one, right? So if you want something like the 90th percentile of x, what's the 90th percentile of that probability distribution? That's all the values x you might see. You want the 90th percentile, but then at 90% below, you can look here at this probability scale, right, between 0 and 1, right, so the 90th percentile, what I'm doing here, 90th percentile. Well, that's defined as the place that probability that x is less than or equal to x, which is the cumulative function, is 90%. You have 90% less, so if you take this point over here, right, and then map it down, this point here is 90th percentile for the distribution. So if you know the density function, you can do the integral and find the cumulative distribution function. Both of those describe the random variable and the chances of different values. If I tell you capital F of x, and I tell you the cumulative, the CDF, how do I get back to the density function? The opposite of the integration, right, is the differentiation. Right? So we can take a derivative, the derivative of the density function, the cumulative, sorry, with respect to x is the density function. With the discrete one, the cumulative function went all along kind of as level curves, and then at a point we had probability, it jumped up. Right? And so to get the probability at a particular point, we could take the difference between two places. You know, how high did it jump at 2? How high did it jump at 3 to get the individual probability? And the continuous version is with derivatives. Right? So let's look at one or two examples of this. Something called a logistic distribution. There's a continuous distribution. And the cumulative distribution function f of x.
Professor?
Yes.
Thank you.
What?
Sorry, I just have a quick question. When you
Yeah.
went back and you took the derivative of
Yeah.
the capital F
Yeah.
function,
Yeah.
what's the name of the capital F versus the lowercase f, the two different models?
So this is going to be the cumulative distribution function. Okay. And this one is a probability density function, or PDF.
Okay.
So one's density, so just the height of the curve, and the one's the cumulative, how, if you're going from left to right, what's the total area up to that point under the curve.
Okay, thank you.
Yeah.
So what's the probability mass function then?
So that's the probability at points for
Okay.
discrete. Thank you. So this particular one, right, is e to the x 1 plus e to the x for x in anywhere on the real line, negative infinity to positive infinity. Right. Graphing this one, it goes between 0 and 1. As x goes to 0, as x goes to negative infinity, this thing actually goes, so at x equals 0, what is it? So if x equals 0, right, then the cumulative at 0, right, the probability that x is less than or equal to 0, in this case, right, it's just e to the 0 over 1 plus e to the 0, which is just 1/2. So this one at 0 is already at 1/2. It starts out and then it comes up and kind of does that S-shaped curve. Different cumulatives will, shoot up faster at the beginning or shoot up faster at the end, and kind of correspond to different things as we'll see. But that one at the midpoint here, the median for this one is 1/2. What's the density function? We want to find that. We have to take the derivative. And so for this derivative, it's a ratio. Right? So the derivative, we have to use the quotient rule, right? This one, there's 1 plus e to the x in the denominator. We square that. And they take the derivative of, we'll take the first thing, 1 plus e to the x, and then take the derivative of the numerator, that's e to the x. And we subtract the numerator times the derivative of the denominator, which derivative of that thing is just e to the x again. So we get a little bit of cancellation. There's an e to the x here, and a minus, so that goes away. And so we're left with an e to the x over 1 plus e to the x squared as the probability density function. So, and that works for all the entire real line. This plot, right, if we want to draw this density function for this one, right, well, the median's at 0. We know from the cumulative that halfway up is 0. So let's put 0 here in the middle. This particular graph happens to look kind of like a bell-shaped curve. It's a little bit different, and it tails what it does in the extreme, but it's kind of like a bell-shaped curve. It's symmetric, about 0. I didn't draw it too well there, but this is the kind of the cumulative distribution function for the net. What's the probability that this exponential random variable gives us value? So 0 is the median. What's the chance between -2 and 2? For this random variable, what's the probability that -2 is less than or equal to x is less than or equal to 2? The density, the f of x function is here symmetric 0. So we're going to ask -2 up to 2. What's the chance that we would get some value in that interval? So, or you do the integral over that space, over that line of the density. And so we could do the integral of this e to the x, 1 plus e to the x, right, squared over that density. Right. The is that what e to the x? Right. This thing ends up being e to the x over 1 plus e to the x cumulative, evaluated at x equals -2, 2. We took the derivative. We started with x, the probability that we're less than a number, which was this function, and so I know that this is the integral of that thing. Right? We did the derivative of this and got this one. The integral goes the other way. I'm not going to worry too much about doing that. But this is the cumulative distribution function at 2 minus the cumulative at -2. So we would get e squared over 1 plus e squared minus e to the -2 over 1 plus e to the -2. We put that value into the computer, right, we'll get the probability we're between a couple points. So down here, the exponent of 2 divided by 1 plus the exponent of 2 minus the exponent of -2 divided by 1 plus the exponent of -2 gives us about 76%. So the probability we're between these two, about 3/4 of the probability time we're going to have value between here, about 0.76. Any questions? So a different example is something that's called a Rayleigh distribution in here. Rayleigh. And so this one is a continuous random variable. Its cumulative distribution function looks like 1 minus e to the -x squared over 2, for x greater than 0, and it equals 0 for x less than or equal to 0. So this is a random variable that could use for a model. It's used for things like wind and other things where the measurements are all positive. There's no probability that it accumulates below 0, and then after that it goes up. Right? So as x goes out to infinity, right? This goes, it's like 1 over infinity. This goes to 0. So then this one goes to 1 as x gets big. Right? This type of density, well, what is f of x? So this is the one we call the CDF, which I usually write in capitals. And this is the probability density function. So again, f of x, the probability that x is less than or equal to a value. So what's the density? We got to differentiate this one. Think about that for. Why don't you try and work that one out? Remember all these rules for differentiating things.
Is it negative x squared over 2? Is that what?
This is a negative x squared over 2. All of that is up in the exponent. A lot of things in probability density can you once live in that e to a power and it can be negative. So if we take a derivative, we're just going to call it 0 for x less than or equal to 0. But here there'd be a negative e to the negative x squared over 2. You repeat that thing, then take the derivative of what's up here, which is just negative x. The derivative of x squared, you get the 2, and that cancels the negative there. So the negatives, it becomes x e to the negative x squared over 2 for x greater than 0. And now it turns out that this density function was positive in the sense that it's 0 down here. At 0. This particular function will slope up and then go down and be kind of skewed. There's a number of different densities distributions that are positive that have kind of this skew thing. And they differ in how fast they go up and how long it takes them to come back down. And depending on the measurements you have, one or the other ones that we'll see might be appropriate. So what's the probability, say you had some number here, like 5. What's the probability that our Rayleigh variable is greater than or equal to 5? How would you want to figure out the chance that you're greater than 5 if you're measuring something that has this distribution? There's a few ways to go about it. Yes?
Can't you take the integral from 5 to infinity?
No, yeah, you can take the integral from 5 to infinity of this density. Right? The x e to the negative x squared over 2 dx. Directly doing that, you really have to use integration by parts. We're not going to do that just yet, right? But that is correct. An integral from 5 going up, we're asking about this area under the curve, under the density, going out forever. Total area is 1, so your answer is going to be less than 1, even though that goes out to infinity. It decreases fast. So that integral is this, right? Is the cumulative. That's less than equal to that, right? So this is really the cumulative evaluated as x goes toward infinity minus the cumulative at 5. The cumulative is 1 minus, well, at infinity, as this goes to infinity, this part goes to 0 because it's like 1 over that. Like 1 over infinity goes to 0, so it goes to 1. So it's really 1 here. And this other one is 1 minus e to the negative 5 squared over 2. So I'm plugging in the 5 here. Did I put a negative? Yes, okay, good. So 1 minus 1 is 0, and minus minus is e to the negative 5 squared over 2. What's that value? Exponent of negative 5 squared over 2 is pretty small, right? Really quite small. So this is about, so 0, 0, 0. How many zeros? So 6 zeros, and then a 4. Oops. 1, 2, 3, 4, 5, and then a 4. It's really small, right? So I probably shouldn't draw the picture like this. I should probably draw the picture with 5, out here someplace, so that the tail of the distribution is, this little tiny part out here. Right? Maybe even farther than that. So 5 with this distribution would be a really unusual point. So you can also approach these problems, right, by taking first 1 minus the probability that x is less than 5. So 1 minus the cumulative of 5. That's essentially what we had over here. But before going to the integral, sometimes you could do the logic of, the 1 minus to get the opposites, and it might simplify things a little bit. If things are stated in terms of cumulatives, right, this is the probability that x is less than or equal to that. So then, right, the probability that x is greater than a number, right, is 1 minus that. 1 minus f of x. 1 minus the cumulative, which in this case ends up being e to the negative x squared over 2. So if you wrote out the integral and then did it, you would get that answer correct. If you see it this other way, if you already had the cumulative, it would just say to the step. Yep.
So why do we find the density function if we're just going to take the integral of it?
So some things, when we will use it in some ways to describe the, what describes the density, it describes the random variables. In some cases, we're going to go up to something where we have multiple measurements of the same variable and then want to see what distribution it is. We're going to have a way of doing that that uses the densities. And the densities versus the cumulative just gives you another graph. Right? So the CDF function for this Rayleigh comes along at 0, and then it shoots up pretty fast and then kind of goes off. This one, shows you the x values and kind of their relative densities. I can kind of picture a little bit better what the values are going to be, right? Where they're going to be concentrated based on that density. So it's just another way of looking at it that gives you a little bit different information. So if you just say where are the x values, the density looks something like this. The cumulative, right? It comes along. They both start at 0. Right? So this is going to be the cumulative one that goes up to 1. This one goes up pretty fast, and then kind of goes out. And the bulk of the values are in here, and so most of this increase is supposed to be kind of this little part here. I did a little bit too steep maybe to make it look the same. So it goes up pretty fast and then asymptotes out here. So most of the values are in this range, right, versus this. And so they both show you where the likely values are, but it's kind of a little bit different interpretation. Right? Once you have one, you just get the other by differentiation. So they both describe things. In a lot of things like survival, a lot of it deals with this cumulative or 1 minus the cumulative. How long does something go before something happens, before it breaks or somebody dies, or time until getting better could be a positive interpreted. So both of them get used, and just kind of going back and forth between them is something that's useful. Right? But any questions about? There's a couple examples. We'll see a number with more specific applications. Right? These random variables, just like our discrete ones, have moments. They have averages, variances, and things like that. Right? So the expected value value of x. We're going to take x times the density. For discrete ones, we had the values times their probabilities. We don't have probabilities at points, we have density at every point. This is another reason for using the density. And then we're going to integrate that over all the possible values of x. When you actually compute this, if it's something like the Rayleigh that's only positive, right, then you really have an integral that goes from 0 up to infinity or 0 up to a range. If f of x is 0 in some area, but generally it's defined that way. If you needed to take expectation of the square of x, then it's going to be, you're going to put an x squared here, f of x dx. If you needed to get the moment generating function, that's brackets, right? Then it's an integral of that particular function times the density. So whatever function of x you have here, it's like that, right? So let's look at some examples. We'll look ahead just a little bit at one particular example. Right? We're going to look at exponential. So an exponential random variable is also a positive random variable. It's in many ways an elementary one that gets transformed to make many more complex things. Yes?
Can you go back to the last slide for
Yeah.
a second? Thank you.
But we'll look at the exponential. We'll start with its density. We'll find its CDF, and then find its mean. So there's going to be a series of kind of some integrals and things. And then do some comparison. So an exponential random variable, a density, it has a parameter lambda. For x greater than 0, and it's 0 elsewhere. So positive random variable. And this density, the f of x density, slopes down. Sometimes it's used for survival times, or measurements of things at a site where there's really kind of a large collection of smaller things, and then a few big ones. Kind of models that a little bit. The density is 0 behind here. What's the cumulative distribution function? So the probability that we're less than or equal to 1. When you take the integral, because the density is 0 before the positives, right? We're going to start at 0. We're going to figure this out for x greater than or equal to 0. And then we go up to whatever our value of x is that we're asking about, right? But this is one of those cases where now we want to take an integral, so I'm going to use something besides x in that placeholder, because I have x 2 places and it's a little confusing. X. So I'm going to put a t in here just as a little placeholder. You can put anything you want, y, or I guess we use t for moment generating functions. So let's just put a y in here as another letter. Okay. So the integral of e to a power is that thing again, divided by the derivative of the thing that's in the numerator up the top. Right? So it becomes lambda e to the negative lambda y, and you divide by the derivative of this thing. So there's a negative lambda in here. Right? And then you evaluate that at the values of y equals 0 and x. The lambdas cancel. One way I think about checking that I've done the integration right, if you differentiate this with respect to y, you should get this thing back, right? So if the lambdas aren't there, you differentiate that, you get the e to the exponent again. Then you differentiate that, you get a negative lambda. Well, that lambda is what you need, and the negatives would cancel, so that works out. We don't do all sorts of functions. We don't do too much with sine, cosine, trig functions in these type of classes. Mostly it's exponent, polynomials, x to a power, differentiating or integrating, or e to a power, differentiating and integrating. We'll see a lot of the same functions over and over again, right? So calculus was a few semesters or years back. We have a few special functions that get used many, many times. So if you review those, it will pay off. If you get comfortable doing some integrals or differentiating those, it will be not a bad strategy. So if you get rid of the lambdas, you get e to the negative lambda x in here, right? And then it's minus, there's minus e to the 0, right? Because y is 0 at the lower side. So it's negative e to the negative lambda x plus 1, or 1 minus e to the negative lambda x. And that's the cumulative distribution function, right? So that's the probability that so for instance, we have an exponential random variable with a parameter of 3 versus an exponential with a parameter of 7. What's the probability that our value that we get is greater than 0.5? So maybe this is survival, time till recovery. What's the chance that it takes more than half a year to get better? For these two things. Well, before answering, right, we have the cumulative, the probability that you're bigger than a value. Right, is 1 minus the cumulative. So for the exponential, it's just this simple e to the negative lambda x. So this 3 here is lambda. Which one of these two is more likely to be bigger than 0.5? Which of these probabilities is bigger? So e to the negative lambda is 3 times 0.5 here, and this one is e to the negative 7 times 0.5. So e to the negative, this one turns out to be about 22% of the time, whereas this one is just about 3% of the time. Yes?
Like what are those, like what are 3 and 7 like telling you? Like what is it, like?
So these are just examples that I've given you, right?
So like in like if let's say it was like survival, like what does that have to do with the survival?
Yeah, so it's going to affect the shape of the curves, right? Right, so here's this curve, what it actually is, how far it actually has any probability, does depend on that. Right? We haven't fully answered it yet, but we can look at it with computing. Right? So for instance, we can make a graph. The exponential is something that's included in R. Right? So or we can just, right, so we can take, say, a sequence of values of x. Sequence is a little function. And we can do 0.001 up to, say, up to 10, and we can do it by little steps, like 0.001. Right? So x is a bunch of, here's the first 2 values. It goes 0.001, 0.002, all the way up to 10. So it's all those values. Right? If we did a plot of x, and then there's a density for an exponential function. We don't even need that, right? It's really, if we use 3 as lambda, then exponential of -3 times x. Right? That was the density function. and we're going to make a little line out of this. That's what this function looks like here. 10 may be too big. If on the other hand we had a value of 3, then this would change, and we can do line type equals, change the line type, make it dots, and so that's there, and we can put them, which one was higher? This other one was higher. So let's do this one first. That's the one with 7. And then we can do the one with 3, but if you do it with points, this other command adds it to it. And so there's this other line. Now, sub 10 looks pretty extreme for any of these. So let's change our range of x. Let's not go that far. Right? Let's go up to about, say, 2.5. Right? For a range of x. Now, if we redo these plots, that's the one with 7. Right? And this is the one with 3. Right? So it's not nearly as steep. Right? So the one with 3 had more probability out in the tail. About 22% was beyond 0.5, whereas when it was 7, it was steeper. So if the parameters are different, if the dark one was the old treatment, they took the governing parameter 3 here affected the rate of survival. Right? If you could do something to improve care and make things better, maybe we'd switch to this other number of 7. Right? In which case, survival happens generally more rapidly. Right? There's more probability under that one. So that this lambda, this parameter, affects these shapes. Right? And it will affect the probability. So if I can try to draw that again, so we get up here to about 2.5, and the one for 3, right, kind of went up like this, whereas the one, so that's the plot with lambda equals 3, and these are the density functions. When we get to 7, right, it was coming out here, going down faster like this. So this one is 7. So when we looked at the probabilities of 0.05, the area under the black curve, the probability that x was, I guess, was greater than 0.05 when lambda was 3, lambda equals 3, versus the probability that x is greater than 0.5, not 0.05. Given that lambda was 7 with different values. This one, as we got before, was 22%. When it's 7, it's only 3%. So about 22% of the time, you're waiting more than half a year. Whereas this one, if you can do something to alter the situation, it's different. Right? So it changes the densities. It changes where the likely values are, how that parameter goes. Right? It's also going to change the average waiting time. Right? So what we're going to do is calculate the expected value for this one. Any questions before we move? Yeah.
Is lambda specific to this example, or because I don't really understand what it means?
Yeah. So lambda. No, thank you for asking. So lambda is called a parameter. Right, and so the value of lambda affects the probability distribution. In this case, for the exponential, the rate of lambda is some number greater than 0. And so if you're in different scenarios, right, you're going to get different values of lambda. Right? Different lambda with survival from stage 4 cancer versus survival of stage 3 cancer versus survival of stage 2 cancer or something like that are different lengths. Right? And so you're going to get different slopes depending on which scenario you're in. And what affects the probabilities through that density function, or through the cumulative, or through the tail area chances, right, that we calculated, is this parameter. A lot of statistics is, you have a set of data, how do you estimate lambda? And again, in that mathematical statistics, we do more with figuring out how to estimate it from data. In this case, we're going to look at different lambdas and see how it affects chances. The other thing that this lambda will affect, we want to take this expected value of the random variable. What's the average survival time? Well, for continuous, we take an integral of our variable x times the density. And that was, lambda e to negative lambda x. Yeah. And the density is greater than 0 only for the positive survival time. So we don't do the entire real line because it's the density 0 after that. Right? So we have to integrate this thing. Right? This one at the end of calculus 1 would be an example where we use integration by parts. So we'll do, this will be useful for a few things. Right? We'll kind of have the same similar scenario for these. So you don't necessarily need to review all techniques for doing integrals of complex kinds. Calculus 1 going into calculus 2 really does a whole bigger set than we are using, but this is one type of example, right? So to do this, we identify one part with kind of part of it, and then another with this other part. If you multiply this u and this dv together, we get this entire thing. And so we differentiate with respect to u, so we get lambda dx here, and we integrate this with respect to x, and so that we e to negative lambda x, and then there's a negative lambda here. And so we replace this integral that was u dv by v du. So there's a lambda e, there's a negative multiplying those last two things together. U times v, I did the wrong thing, right? So there's an x lambda times the negative e to negative lambda x. Lambda, that's evaluated at x going from 0 and infinity minus the 1 at 0, minus the integral. Instead of u dv, then we do this v du. And so there's I'll write the v part first. That thing times this one, which is lambda dx. Now, if you like applied calculus things, this is kind of fun as well. This term is all 0, actually. Because at 0, there's a 0 here, right? So that at the lower limit it's 0. The upper limit's in 0 as well, because there's a x, which is infinity, but this one is like 1 over, right? Because the negative exponent is like 1 over e to infinity. And that one is bigger, so it's something called L'Hopital's rule for finding out that limit of what that thing is. But it's actually 0. Again, for most of the applications, you won't have to do a lot of this, but that's how it goes. And so then this one, the lambdas cancel, the minuses cancel, so it becomes a plus. And so it's 0 to infinity e to the negative lambda x dx. So the point of this integration by parts, it takes this integral into one that's easier to do. Right? And so there's an e to the negative lambda x, and then there's a negative lambda here, and that's the integral of that thing. And evaluated at x going from 0 to 0. At infinity, this thing again is 0. And then you take a minus, and at 0, e to the 0 is 1, So it's negative 1 over lambda, so it's just 1 over lambda. That's the average time until the event occurs. So lambda here, 1 over lambda is actually the average of x. So if you had a different distribution, a different process, you're waiting someplace and the bus takes 5 minutes, as an average the parameter would be 1 over 5. On the other hand, if it takes 10 minutes, on average, the parameter would be 1 over 10, and it would change the probability. Right? So that's the average value. But any questions? This particular example used a little bit more techniques from calculus to do that. In other times we'll have things that are polynomials, and it's not as hard to do. Now, if you want the variance of x, we would take expectation of x squared minus expectation of x, quantity squared, and then this expectation of, for this exponential, the expectation of x is lambda. The expectation of x squared, we would take an integral from 0 to infinity of now x squared times the density, lambda e to the negative lambda x dx. You would figure that out by integration by parts twice. We're not going to run through it. It turns out that the variance of x is 1 over lambda squared. So the standard deviation of x, right, is 1 over lambda. So as lambda gets big and things happen rapidly, so you don't have to wait very long, the variance goes down. You get, like with 7, everything was more concentrated towards 0. When it was 3, it was more stretched out, and you get a longer range of things. So if we had a, yeah, anyway. So that means that this thing, if you did this calculation and did this integral, well, this equation up here means that it's the variance of x plus the expectation of x, all of that quantity squared. So if the variance is 1 over lambda squared, and this is 1 over lambda, and quantity squared, this thing should end up being just 2 over lambda squared for that second moment. So if you went through directly to do that, that would be the answer that you would get. Right? But I'm just telling you the kind of conclusion that the variance is 1 over lambda squared. Right? So let's say you had an integrated circuit. And the lifetime of this circuit is modeled by an exponential random variable. And the average lifetime is 3 years. What's the probability that the circuit lasts 1 to 3 years? What do we know based on this so far? So if the average is 3, what's lambda? So then the average, right, like we did in this one, right? ends up being
Oh, 1
like
over.
1 over. Got it's inverse. That's how this, you can change how you write the density to make it equal to the mean, but our book and some other books do, 1 over. Right? So if the expectation of this random variable is 3, that's 1 over lambda. So we're going to use lambda equals 1/3 as our parameter. And so what we want to, the chance that its lifetime is between 1 and 3 years, and we want between 1 and 3. If we know that, so it could be an integral. Right? We could write down an integral and do that. Right? We could write down the integral from 1 to 3 of the densities. Now it's lambda e to the negative 1/3 lambda x. This is also, right, the probability that x is less than or equal to 3 minus the probability that x equals 1. If you think about taking less than or equal to 3 and then chopping off the lower parts, this is the cumulative distribution function at 3 minus the cumulative at 1. The cumulative for this was 1 minus e to the negative 1/3 at 3 minus the cumulative 1 minus e to the negative 1/3 at 1. And so this ends up being point greater than, so it must be 1, my notes are a little backwards, 1/3 over there, 1 minus, well, I'm going to write it. So the minus minus is e to the negative 1/3 minus e to the negative 1, right? The 1's cancel. And 0.717 is that value, 0.368 is this value, and so the difference is 0.349. So about 35% of the time, that circle is going to survive between 1 and 3 years, if it's exponential. Okay? So that's the type of thing that we'll be doing with continuous distributions. We'll look at some others. There's many different examples of ones. We'll look for ones that are positive random variables. If you go to this NIST statistics, this gallery of distributions, that's here through the Engineering Statistics Handbook. These are all different types of continuous distributions that can be used for different things. Our normal bell-shaped one arises many times, distributions of averages. T and F are special functions, the chi-square, that come from random samples and taking averages or standard deviations. Here's the exponential formula. It does it a little bit differently here. It does 1 over beta. We just do lambda, which is kind of 1 over that. Consequently, the mean is just a little bit different, right? Right. But yeah, here's the density function, the cumulative distribution function. It rises pretty quickly because a lot of the probabilities at lower values, and then it trails off, so it goes up slowly at the end. But then there's different functions that get used, and I think down here it talks about usefulness and reliability. It talks about estimating things, and maybe it has a numerical, well, in any case, some places in here there's numerical examples of things. But other ones, we'll also look at this beta distribution here eventually. Beta is special. It's the probability you're between 2 points. The main application of that is you're between 0 and 1. So beta gets used as a model. Say you had all the school districts in the United States, thousands of them, and you're asking information about what % of the students are immunized against measles. Right? It could range from 0 to 1. Maybe 80% of the students are generally immunized, but different school districts will have some variability. So that model, that beta might be a model for something like that. So we'll look at different ones. To do that, we'll look at probability density functions, the cumulatives, means, variances, to get some idea of different models, calculating probabilities, applications of that. This exponential, it's also possible to take random samples of that. So helping, if you do there's an exponential, there's a density function, a cumulative function, a quantile function, and then taking random numbers. Right, so a rate in here, it shows you it's using this form, that's our form, that's exactly what we want. Right? So if we take a random sample from an exponential, say we take 10 values, and our parameter is 1/3, we're getting values like this. Right? For that, oh, we got 15, sometimes you get large values there. Right? If you take a whole bunch of values, say you take 10,000 values or something, the mean, what should the mean be? The mean should be about 3. Right? So it's matching that. If you take a histogram of a bunch of values, right, then the survival times roughly are like that distribution. Standard deviation of that is also about 3, so the variance about 9, depending on the random sample that you get, and right. But how do they actually generate these numbers, these random samples? That so the cumulative distribution function for this one was 1 minus e to the negative lambda x for an exponential. So this kind of goes up fast, and then it goes out like this. This is the cumulative distribution function. Right, the height of this is between 0 and 1. 0 is less than or equal to f of x. 1. So if you wanted to get one random value from this distribution, there's algorithms for generating a uniform. We haven't really talked about what a uniform is exactly. We will when we come back after the exam. So a uniform value gives equal chance for any values between 0 and 1. Right? That's actually constant density. And there's algorithms that are studied in number theory and other things who are generating these things. Right? So what they really do is take a big, huge prime number and then multiply it. Start with some number, multiply it by a big prime number, add another prime number onto it, and take a remainder. And there's a pattern to it. There's a sequence of numbers, but the digits that come out of those remainders have a very long period. They don't repeat in any pattern for billions and billions of times. It's something that they work on in number theory to figure these things out, right? And so those remainders look, for all intents and purposes to us, as if they're random. They have about equal spread between all the intervals that you might have on the line. It doesn't favor one digit over the other. So you can generate some random value, say u between 0 and 1. And then if you take that random uniform between 0 and 1 and then map it over to here, and then map it down, that's where you get your random x value. And so if you generate a random uniform number and you get some number u, what this is doing is setting u equal to our cumulative distribution function for x. Set that equal to f of x. And so in this case, it's 1 minus e to the negative lambda x. And then this process of drawing this arrow, of going to the cumulative function and down, is inverting that function. Right? It's solving for x. So from this, solve for x. Right? So if u equals that, that means then that, well, if you put the e to the negative lambda x on this side, add it to both sides, subtract u from both sides, you get 1 minus u over here. Right, then we're going to take logs, natural logs. Right. Well, natural log of this thing is just negative lambda x, and then log of 1 minus u. Right. And then divide by negative lambda. Right? So x is going to be 1 over negative lambda log of 1 minus u. Right. So if you generate a whole bunch of uniform numbers, u1, u2, up to un of them, and do a transformation where the ith one you take the negative 1 over lambda times the log of the next one of these, then you're going to end up with values x1, x2, xn, and these things are going to follow an exponential probability distribution. So it's actually using these cumulatives to go back and forth between some distributions, and so you can generate things. So let's see if it works out. Negative, let's see if I have that written down. Can you remember it? Maybe I can. So anyway, let's see if we can remember it. Negative, right? So generating uniforms, right? So let's say we take a random sample of uniform, and say take 100, say 10,000 of those values. The uniforms between 0 and 1. 0 and 1, here are many, many different, it's like going by 0.05s, about 20 different bins. They're pretty roughly close to even, right? Any numbers between 0 and 1 are kind of equally likely in here. Theoretically, this distribution that we'll see later, right, is flat, even across. But to do this transformation, say with lambda equal 1/3, right? We need to take the natural log of 1 minus u. Log in our default is that. And there's a negative, right? And then we divide by the parameter we want. We need to divide by 1/3. It changes all of those. Now the histogram of x looks like that. It's sloping down like an exponential. The mean of x, if it is exponential, it should be about 3. The variance should be about 9, and it's pretty close. Right? Little random variation. Right? But we can go between, this cumulative allows us also to go between the variables. Right? So what have we done? Right? So to kind of summarize what we've done so far, we continue continuous random variables. We've looked at there's a density function, probability density function, or PDF. There's a cumulative distribution function, or CDF. We've calculated the expected value, and well, at least talked some about the variance. Right? And we've used different techniques at looking at the probability that x is between some values. And often in these, there's a parameter, lambda for the exponential. Other names for these others, for other ones. And there's some role of the parameter. It changes the shape, it changes the probabilities. Right? Now, when we did discrete, we also had parameters too. Right? Like a Poisson distribution had a rate. Right? And so that was written in generically as lambda or maybe mu. Right? And so as you change that parameter, right, something that happened as mu went up, then that mean went up, the variance went up, and the chance of having large values went up. Right? So in the discrete ones, binomial had a probability p as a parameter. As you change that, it changed the probabilities within that model. That's really what I have for what we need to do for today. I'll post some practice problems. We'll talk about some of those on Thursday, and then homework due on Thursday as well, and talk about what will be on the exam, like format and things like that.
Apologies. Email you got.
What email?
Meet the candidates tomorrow.
I saw, I could do mine. Thank you.
Yeah, fine.
Definitely.
I'll take the email one more. Are you gonna let us know?
Yeah. I just like.
Thank you.